This cube, which measures 2 inches on each side, had been seen before in a photograph. It was believed to be part of the German nuclear reactor project. In Garmisch-Partenkirchen, it's been claimed that children once played with uranium cubes. A mysterious phone call reignited a decades-old puzzle, awakening a chilling mystery dormant since World War II. A physicist received a small dark cube along with a cryptic note that suggested a connection to the Nazi era. The cube's weight, coldness, and radioactivity pointed to a troubling origin. It was believed to be one of 664 uranium cubes created by Nazi scientists during their efforts to develop nuclear technology. After the war, the cubes disappeared. Now, some are reportedly resurfacing in unexpected places, raising questions. Where are the rest? Who possesses them? What is their significance? And why are scientists concerned? The cube that reignited this interest appeared on a hot August day in 2013. Physicist Timothy Koeth, an associate research professor at the University of Maryland, was out for a jog when he received an unexpected call from a longtime friend who asked to remain anonymous. The friend urged Koeth to meet him immediately in a nearby parking lot, piquing his curiosity. Upon arriving, Koeth found his friend standing by a car. The friend opened the trunk to reveal a small satchel. Inside, wrapped in paper towels, was a heavy dark metal cube roughly 2 inches on each side. Its surprising weight and charcoal black surface, marked with small notches, stood out. Accompanying it was a note resembling a ransom letter that read, "Taken from Germany from the nuclear reactor Hitler tried to build. Gift of Neininger." Koeth, a collector of nuclear-related memorabilia, immediately sensed the importance of the object. He suspected it was one of the uranium cubes produced in Nazi Germany during World War II as part of their attempt to develop a nuclear reactor. In 1945, Nazi scientists were attempting to build a functioning nuclear fission reactor. These cubes were part of an experimental setup in Hagerloch, Germany, where scientists including Werner Heisenberg arranged 664 uranium cubes in a chandelier-like structure suspended in heavy water, trying to achieve a self-sustaining nuclear chain reaction. Reports suggest approximately 700 cubes were submerged in heavy water during the project. Intrigued by the cube's potential origin, Koeth began researching its background. He concluded that the reference to Neininger likely pointed to Robert D. Neininger, a metallurgist who had worked on the Manhattan Project. Further investigation revealed that Neininger had once possessed a uranium cube, which he may have given to a friend. Koeth teamed up with Miriam Hebert, a doctoral candidate at the University of Maryland, to analyze the cube and determine whether it truly came from the Nazi nuclear program. What they found next raised concerns. This unexpected encounter with a relic from a dark chapter in history not only renewed interest in the Nazi nuclear effort, but also raised new questions about the fate of these uranium cubes. Before the bomb, how pre-World War II science discovered nuclear power. In December 1938, a groundbreaking scientific discovery quietly reshaped history, though few understood its implications at the time. German chemists Otto Hahn and Fritz Strassmann, working in Berlin, bombarded uranium atoms with neutrons. Instead of creating heavier elements, as expected, their uranium samples split into lighter elements, such as barium. Initially confused, Hahn reached out to his longtime colleague Lise Meitner, an Austrian physicist who had recently fled Nazi Germany due to her Jewish background. Now in Sweden, Meitner reviewed Hahn's results with her nephew, physicist Otto Frisch, over the 1938 Christmas holidays. Together, they realized that the uranium nucleus had undergone fission, splitting into 2 smaller nuclei and releasing a large amount of energy. Meitner and Frisch published a paper in early 1939 explaining the physics behind Hahn and Strassmann's findings. The scientific community, and eventually the wider world, would never be the same. The energy released during nuclear fission was enormous. Using Einstein's famous equation, equals 2 E equals mc 2. Meitner and Frisch calculated that even a small loss of mass during fission would produce an immense amount of energy. This implied that, in theory, a chain reaction of fission events could lead to an explosion far more powerful than anything previously known. Physicists around the world quickly recognized the potential of this discovery, including Danish physicist Niels Bohr. A Nobel laureate brought news of nuclear fission to the United States in January 1939, just as tensions in Europe were rising toward full-scale war. That same year, physicists in America began replicating experiments and confirmed that uranium-235, a rare isotope of uranium, could sustain a chain reaction. If refined and properly controlled, it could produce additional fissile material plutonium-239 and uranium-233, besides the original uranium-235. However, the timing was alarming. Adolf Hitler had already annexed Austria, and Europe was on the brink of war. Germany, home to some of the world's most accomplished scientists, many of whom were Jewish and had fled, now appeared capable of harnessing this powerful new science. A frightening question began troubling physicists. What if Nazi Germany built an atomic bomb first? This concern prompted urgent, confidential discussions among scientists, especially in the United Kingdom and the United States. In March 1939, Hungarian physicist Leo Szilard, who had long been concerned about the military implications of nuclear energy, began writing letters warning governments about the risks. By August 1939, he co-authored a now famous letter with Albert Einstein to President Franklin D. Roosevelt, warning that Germany might attempt to develop nuclear weapons. Roosevelt responded by forming the Advisory Committee on Uranium, a small government body that would later evolve into the large-scale Manhattan Project. Meanwhile, Britain began supporting its own nuclear research program, known as tube alloys, though wartime shortages limited progress. In Germany, the Kaiser Wilhelm Institute in Berlin began investigating uranium and chain reactions under physicists like Werner Heisenberg and Kurt Diebner. At first, the scale and urgency of nuclear research were not fully appreciated by governments. The science was complex, and the industrial means to enrich uranium or produce plutonium were not yet in place. But by the early 1940s, it had become clear that nuclear fission was more than a scientific breakthrough. It was a potential weapon of immense destructive power. As war engulfed Europe, the scientific community split. Some rushed to build a bomb, while others feared the consequences of such a weapon being used. In Germany, something covert and potentially dangerous was beginning. Motivated by the discovery of fission and guided by Nazi interests, a secretive project emerged, the Nazi nuclear program and its efforts to build an atomic reactor. In hidden laboratories throughout Nazi Germany. Away from the destruction of World War II, a small group of elite scientists worked on something they believed could change the war's outcome. It wasn't a bomb, at least not directly, but a machine. A nuclear reactor. Germany's nuclear program began quietly in April 1939, just months after fission was discovered and shortly before Hitler invaded Poland, igniting the war in Europe. The effort was led by Werner Heisenberg, a Nobel Prize-winning physicist known for his work in quantum mechanics and the uncertainty principle. Working with Kurt Diebner and other German scientists, Heisenberg oversaw what would be called the Uranverein, or Uranium Club, Nazi Germany's secret nuclear research group, while the Allies, especially the US and Britain, would later focus on building an atomic bomb. German scientists initially aimed to develop a working nuclear reactor. The idea was that a reactor could produce plutonium, an alternative to uranium-235, which could then potentially be used in a weapon. But first, they needed to achieve a sustained nuclear chain reaction, a continuous release of energy from splitting uranium atoms. To do this, they needed two essential materials: uranium as fuel and heavy water as a moderator. Heavy water, deuterium oxide, slows neutrons, increasing the chance of fission in natural uranium, which contains only about 0.7% of the fissile isotope uranium-235. This is where the uranium cubes came in. German scientists created solid cubes of natural uranium, each roughly 2 inches per side and weighing about 5 pounds, 2.3 kilograms. These carefully crafted cubes were designed to be suspended in heavy water inside a reactor core. Though not weapons themselves, they were critical components of an experimental nuclear reactor that could theoretically produce weapons-grade material. A total of 664 uranium cubes were manufactured. The largest known group, about 400 cubes, was used in the most advanced Nazi reactor experiment, conducted in Hagerloch, a small town in southern Germany. There, in the basement of a church beneath a medieval castle, the Nazi nuclear effort reached its peak.